Go for it. Okay. All right, we're getting our technical situation set up. So thank you all very much for coming. And welcome to the 50th Geoscience Day. I'll admit, so first off, we have quite a few alumni here in the audience. Thank you all very much for coming and for joining us. We gather here together today to celebrate primarily our geology students who are graduating, finishing up their research projects, and soon to graduate here from IUP. It's also, so we thought, our 50th anniversary, or 50th Geoscience Day. And I pulled out we have printed copies of nearly all of our Geoscience Days. They're actually on the shelves just outside by the donuts and coffee that some of you clearly missed. You're not, doing them right now. In the back. So it's those alumni who graduated and presented at Geoscience Day. You should go find the one that you're listed in. This will be at the first. And when I was looking at this morning, I realized the first was in 1975. And if we do the math, in 2024, that's actually 49. So we either skipped a year, skipped a number at some point in the past, and we need to celebrate this all over again next year, or we doubled up at some point before my time. And so we're going to have to do some investigation into this. But as Steve said earlier, geologists aren't great at quantitative things, so, you can't really blame us. Okay, but seriously, thank you all so much for coming in and for joining us here today. We have a special treat for you here this morning, really a couple treats. We have a couple guest speakers, alumni and faculty. Dr. Joe Clark will join us here first. Joe was a student. He did his bachelor's and his master's at the University of Texas at Austin. And then he did his Ph.D. at Stanford. I don't know if you guys have heard of that university. It's a small university on the West Coast in 1966. And I believe from conversations with him, I believe he traveled the world for a little while. And then he started here at IUP in 1972, and I'm trying to track down when he retired, and there are multiple dates throughout the university and on the internet, and it sounds like maybe he retired twice. Something happened in 2004, something happened in 2009, but he had a very long and illustrious career here in the Geoscience department. He was part of the first Geoscience Day, having joined the department in 1972, and then the Geoscience Day beginning in 1975. And so we've invited Joe here today to say a few words just about the early days of the department, or his time throughout here at IUP, throughout his career, and or the beginning of Geoscience Day, whatever he wants to talk about, because it's Joe Clark. So please welcome Dr. Joe Clark.
You wonder why I'm using this cane. I went over to ice, climbed the three highest peaks in Japan. I came home and fell down the stairs. I don't have an elevator. It's great to be here. I hope everyone can hear me. I don't like microphones. You hear me in the back? Oh, good. Okay. Yeah, I remember 50 years ago, Granada. Dr. Walter Granada, he was chairman of the geology department, geology then. And I still am a geologist. I'm about more work at the USGS. Celebrate my 90th birthday. You got to keep after this thing. And geology was my first love, and it shall be my last. And good to see each and every one of you. That meeting we had here, we met in the planetarium. Now, I guess we have a newer planetarium. This is the first time I've seen the building. I wandered all over here to see a single geoscience space. But that first day was great. At Walter Granada, there's a room or something here named. Is it upstairs? There's a lab? Teaching lab. Teaching lab. And what was great, he organized this, and then we added to it abstracts. The whole file of them, but I think they went the way of Walsh Hall. Actual office. Still doing some work with the USGS, and I hope to get out there in the not too distant future. Section with the Omagrada earthquake. We did the planning of the earthquake, and then some other good people did a physical setting. I was professional. Last one that actually had a folding map at the back. Now we all have printers and print off maps. But it's great to be here. Started Geoscience Day, and I don't know when we added text to it, but that's a worth addition. But I had them all until Paul Schroll went with nothing. But we added the abstracts. Talks kept getting better and better. I don't know when we started with the abstracts, but they got better and better. To figures or whatever. Read scrutiny of the abstract before you write one, and then bring it by, and we'll go and read it. So that seemed to work, and great to be here. Covering this building, I've been all over looking for Geoscience Day. I haven't found one yet. Go sign you. Oh, here it is. That's one behind me. Great to be here, and we remember Walt. He did a great job. He was the father of Geoscience Day. It's appropriate we have a lab here to answer. Good to see all of you. This crowd is down from what it used to be, but geology will stay for this. Thanks. It's good to be here. I look forward to hearing some of these talks today. Thank you. Thank you.
Thank you, Dr. Clark. Really appreciate that. And according to the first program, you guys did the abstracts the first year. Because the first few years you had like a technical session and then you had an abstract. You had two booklets. But that's I believe you did it right from the start. Thank you, buddy. That's fair. Completely legitimate. All right. Our next speaker is an alumni from the department, a good friend of the department in the university. Tim Seika graduated from IUP in 1973. He came before Geoscience Day. I don't want to put any ages or numbers on him personally. You won't find him in the abstract because he was just a year or two before. In 1973, he graduated. He started his career with Exxon in 1975 as an exploration geophysicist, working primarily in offshore California. He then moved basically around the world, moving into the Gulf Coast, working in New Orleans and Louisiana, along the Gulf Coast as a production geologist, moving into supervisory positions, basically kept getting promoted. You'll see that kind of throughout his career if you look through his career. He's continuously and regularly promoted. 1993, when Exxon created the Exxon Ventures Company, he became VP of Exploration and traveled extensively really throughout the world, but Azerbaijan, Kazakhstan, Russia, Turkmenistan, among others. He's got some fantastic stories about his time in other countries. They're fascinating. He became the vice president of the Caspian Middle East region with the ExxonMobil company, exploration company, excuse me. And eventually, he was the president of ExxonMobil Exploration Company, which he retired from ExxonMobil a few years ago. As I stated, he's been a very good friend of the department and of the university. He has not, as far as I can tell, has not slowed one bit in retirement. He is part of our IUP National Science and Mathematics College Advancement Committee. He works on our national campaign for IUP to help raise funds for the university. He's also an IUP trustee. I mentioned he's a friend of the university. Those are some credentials to back that up. Tim Seika, he's going to speak today about sort of geoscience through the ages, I believe, how it's changed just a bit. So,
well, first of all, I was born in the place a little before the place. Just saying, not exactly here I want to admit to. So, I brought this today. And I want to talk a little bit how things have changed here. So I have this gorgeous bag here. So believe it or not, mostly for you guys, because they know. This is my original rock hammer. I have put it in a bag because, you know, security frowns and carrying cameras around the campus. My original running campus, and I have to admit, a new case because the old case leather just dissolved. And you know, you guys are into satellites. I mean, things that, you know, stuff on the roof that he shows about the whole world. I don't know if you even know what those, they don't even stand up. These were mine. In reasonably bad shape. So, and I have a book that I'll get to in a second. So, you know, we did a lot of field work. I didn't have enough money to go to field camp out in the West. So, Dr. Hall assigned me to a quadrangle about 20 miles. I mapped and you know, he didn't tell me when he assigned me to the quadrangle that it was beside a game reserve. So when hunting season started, going to the field was quite interesting. But there's a gentleman over there who just spoke, who was who changed it, probably changed the course of life because I took just marvelous. But I was telling him I you know, I want to go for my master's degree. Where should I go? Well, he went to the small school in Austin. And Dr. Folk, I don't know if everybody still reads Dr. Folk. That I should take a course or two from Dr. Folk. That changed my life as well. So thank you. From there, it was a popular school for the local. Had 15 interviews. And you go to work. So I picked a small company. I wanted to go big, so I went to Exxon. And I was particularly interested in cyber because I, at the time, thought I was a pretty good hotshot structural guy. Well, in my PA at University of Texas, I got the structure class, right? The juniors and seniors. I'm like 1 year older. They asked really good questions. I had to go home at night and study on the topic I thought I was a hotshot on. So I still claimed to be a hotshot, and I went to the company and worked in offshore California. And they assigned me to a gentleman, partner with Bill, who was on the research side. He was the hotshot structural. Now, to put the timing in perspective, 73, around 72, I can't remember. That's when plate tectonics became real. And at that point, when I joined the company, we needed to remap California. And we had tons of offshore data. We had very limited country. So it was the greatest boondoggle field trip of my life. We were assigned to visit all the universities up and down the West Coast to get maps, theses, whatever, so we could get onshore data. That part was fun. 5 months after that, to try to integrate all that and hook that to our offshore map was a little bit more work. But Kevin and I then presented to our chief geologist, who's soon retired. Didn't believe. And so we were talking piercing points. Conglomerate in California called the Powell Bay. Very unique set of mixture of rocks. I mean, unique enough that it's a piercing. And I think, if I remember right, 70-mile offset along San Andreas. So he's one of the speakers, gentleman named John. I won't give his last name. John presenting this, and we're all sweating because it hasn't gone very well so far. And chief geologist, yes. So a beautiful mahogany, as long as table. John goes in the back, pulls out a bag, kind of heavy. And he does this. And it's full of the poway. And these odors and jet bells are rolling down the mahogany. In the back row, guys, we're doing everything we can not to laugh. And he pulls out another bag, and everybody goes, "No!" And he sets it up on the table. And the chief geologist was stuck. There it was, alive, piercing. Well, luckily for the rest of us, he retired soon. So, plate tectonics took care of changed everything. Well, terms shortly after that are explained in multiple chapters of Geoscience were vanquished from the geologic language. Then the terms for plate tectonics started. Okay, so what else has changed? Well, first of all, although you still could use those stereodots, will now have marvelous, marvelous detailed satellite. Yes. Electromagnetic, I think they had them during the day, because the university couldn't afford one. And then all the other wonderful equipment this building has in it. All that has changed, how we can analyze, how we do all the different things we're capable of doing now. In my world, in Seismic, the first data I saw was called single fold. It was, I mean, it allowed you to use your imagination wildly because data was less than great. And then they came up with 12-fold, 24-fold, ended up around 60-fold. And then all that was thrown out, and we did 3D seismic. And three-dimensional seismic. When I left, some people called them caves. We had a room about this size. You cut out the dark part over there. And in the back was what was called a driver, who had a multi-screen setup. And we wore special gloves and glasses, and we could manipulate the images by just moving our hands around. And that became a tool that literally changed maps. Saw things we never saw. We were able to see with more and more compute power, we were able to see it. So you saw something interesting. In a couple of seconds, it just churned away. And everything that looked like that image in the 3D is highlighted. You instantly could see, do they look geologic? And they So the thing that then opened up the oil industry and stratigraphy was the discovery of these gigantic deep sea canyon cuts that were half a mile deep off the continent, tight channel, and then a beautiful deep sea canyon. Look just like so we ran all kind of models. And it turns out geology does that. Nature does that. It's the same pattern over and over again. Except now with the 3D survey, we can see the levees, literally see the levees on the side. All the still over the fans. And then of course, oil, and usually these fans were they needed the rocks to be relatively young before they got too hard. Density, velocity difference in seismic for oil and gas. They would create amplitude in them, large amplitude, which became nicknamed bright spots. The real name was DHI, direct hydrocarbon indicators. Well, in these fans, you could literally see the pockets light up. And as you went back up the channel, you could see where the channel shallowed out. We've had a fan shape for your feet. All lit up for it. I mean, it was, for us, it was fabulous. As soon as the data got better, it got. So we were mapping things. When I first started, field geologist going up to the North Slope on foot, doing the mapping. Now we will point. We got all the data. You have all the satellite information. You just pick spots to go out. Yeah. So revolutionary is what we thought, even in terms of how basins were formed, how things were deposited, because we were able to develop models of when things spread open. And in my business, source rock, a good organic shale, they come at certain times on low stands. And we could now model where those low stands were in basins that had never been drilled. And you also, so it was a revolution. I'll tell you one last story. This was one of my documents. I believed in all the way back to the founding geologist for Exxon was Pratt. Pratt actually worked. Only geologist worked for Rockefeller. He wrote a pamphlet. I didn't have the pamphlet here. I wrote a project. The pamphlet's about 8 thick. That's the total of petroleum geology written by Pratt. He said, if you get good acreage, net lasted all those years, and the guy was president did the same thing. Here's some acreage in Ghana that was offshore, that was under conflict between two countries about where the border was. So legally, it's called force majeure. We in shell with 50-50. We pay our rental into a bank account, hold the money for the government to settle it. So it finally got settled, and we pulled out our data. We just held this thing for 30 years. So guess what the data was? Single fold. I mean, we waited 30 years, and now we couldn't see it. So we in Shell decided to do the sample 3D survey. And under anti-competitive laws, we each get raw data, and then we do our proprietary process. We can't share it. And then so on the very bottom of the map, and so Shell, they were on the meeting, they said, well, we'll show you our map first. They showed the map. There's no in the bottom of it. So our guy went, yeah, that's really interesting. Put his arm right across the bright spot. Yeah. We think we should shoot another 3D survey, maybe to the south. And they talked about impact. Shell said, no, their management told them they were out. And we said, well, if you're out, we want all your equity. But I said, absolutely. What's their 50%? Walked away. We shot a 3D survey and another 3D survey. We drilled 6 1 billion barrels. All deep and sitting on a low structural. There are a few images that were passed between the companies. But we waited 30 years for that. So, and the other thing is P6 skin. I'm sure the pictures you're going to show us at the Clock Studio are wonderful. I'm going to find new data. That's the whole evolution of geology, right? Make a map, what is the data you have, you make a theory, you do a lab test, what is the data for? the V6 schemes. And never give up on chasing the idea because it could fruition. So with that, I think the world of science is changing its impact on the global world significantly. Taking my stuff back, but in fact, anybody that wants to book, thank you.
You too. I don't know why I'm standing. We're actually on time for once to get started, but now I'm turn over to Dr. Coles, our MC, for their presentation here.
Hello, everyone. We're going to take just a minute to make sure the first presentation is set up, so we'll be back. Thank you for your patience with the clinically inept or digitally inept like myself. I remember reading Cloak Carbide in class, and I'll give some stories about the synclines later. All right, I'm Ken Coles, and we have senior presentations. Today we're going to start with Kyle Oshenic, who will tell us about any investigations of road salt impacts on Indiana streams.
All right, as Dr. Coles just said, my name is Kyle Oshenic. I had the pleasure of working alongside Dr. Farnsworth this semester on exactly this, any investigation of red salt impacts on Indiana streams. Specifically, we focused on one location. It was McCarthy Run. We got right here is indicating exactly where we pulled data from. And this is just another view of where the data is. Okay, so McCarthy Run is the sub-watershed of Soda Run. Basically, but so these are the data loggers that we had used. They're called Sonic data loggers. They measure 3 different variables: temperature, water level, and water conductivity. They're actually like pretty little. They're on here somewhere, I think, like on there somewhere. And these are them in the stream. Like I said, they just measure these things. So basically, though, through data, it needs to be corrected and converted. But they're not like it changes. Variables change. So then it takes people like Dr. Farnsworth and I to go in there and analyze this data. And based on previous research Dr. Farnsworth had conducted with other students, he was seeing that there was a spike in conductivity in these Sonic data loggers. But she then approached me because I needed a project to do so I could graduate. This right here is a data sheet from Three Rivers 2 streams in Allegheny. And I'm just using this picture because it's going to show you guys basically that even in an Allegheny stream that, yes, milligram per liter is pretty high there. So anything above 230 is considered unsafe to drink. And anything over 1,000 can actually stunt fish's or fish growth. Any kind of ecology getting on. I actually see a lot of this going on in Indiana streets like that. So basically, this is one of the first methods that we did. We had to use the already recorded conductance level or conductivity level with the Volcanoes data loggers to get the specific conductivity. And this is the equation that we were given on the references that we used, right? So this is the specific temperature that it gave us already, and just minus by 25. After we did that, we were able to convert our specific conductance into TDS. But I'll show images later that help, visualize the representation of what I'm trying to explain. And right here, this is a correlation factor that we use, is between 0.5 and 0.8. Based on some reference that we got off the internet, and we use our specific conductivity to create our TDS for graphs that we're going to I'm going to pull up here shortly. This is where it gets a little bit crazy. So this right here is a rating curve. And it basically shows the characteristics of the stream, specifically McCarthy Run. Over here on the left is the channel depth and then channel cross-channel distance. This measures the discharge at certain times. So we had to use Manning's equation after we created these gradient graphs to create this polynomial for discharge. The Q is equivalent to discharge, N is equal to the roughness coefficient of the stream bed. A is the cross-sectional area, R is the hydraulic radius, and S is the slope of the channel. I have a animation showing specifically where dots relate this bed. This is the curve that was created. Thank you, Dr. Farnsworth. And this shows discharge at certain channel depths. So basically, as there is deeper water, we get higher discharge, right? It gives us information to use for hysteresis and time series charts that I'll show later, related to McCarthy Run. Right here is the time series graph. Blue would indicate water level. Red indicates TDS. This would be a summertime event, and this would be a wintertime event. So, as a rain event happens, water level increases, and then TDS decreases because it dilutes. On the right is a wintertime event, so road salt is being introduced into the streams. So a rain event occurs, TDS spikes, and dilutes. And I'll use this with my actual data from McCarthy. I'll introduce it right now. So this is a hysteresis plot, and you'll see with hysteresis plot that we've created that the rain event occurs, and you can see the data. It sort of does this, and that during a summertime event, and during a winter event, you can see that the data will have a spike in TDS versus discharge. And now indicate a road salt event. So I have the little circle going on, dilution event. So we'll get into some of the data. These are two contrasting examples of a time series graph, similar size rain event at a specific location. So once again, blue is indicating water level. The orange or red is indicating gas within that stream. This is a summer event. This is over a period of 5 days. You can see that there's a rain event that's occurring as water level seems to rise drastically. Within. We can see a dilution event occur. TDS. That's a summer event, and the contrasting example of it would be a winter event. Same thing here. So we have rain being introduced into the stream, and it's also introducing with that a lot of salt or whatever else is causing the spike in conductivity. And then we are seeing a little bit of dilution happen. Nothing compared to this. As you can see, we have 500 to what is that? 3,500 milligrams per liter during our winter event that we're recording from the data, right? And this is our summer. Milligrams per liter. So remember how I said anything above 230 milligrams per liter considered unsafe for drinking? We're going to see in one event right here that's already above 230 milligrams per liter the entire time away, in 2019 at least. Once again, these are two contrasting examples for hysteresis plots. Blue on the left of summer 2019 indicates a before rain event. This is during the rain event, so we're getting dilution. This is after rain event, so it's returning back to normal. Same here, summer 2019. So we're seeing blue is before, and the rain event occurring. We're having that spike in TDS all the way up to 3,000, which is a lot, especially when it's getting formed at that fast. And Turning back down to here, so it's a dilution event now. It's returning back to normal at the regular TDS level. Just a little bit of conclusions that we're going to start drawing about now. So basically, off of those two contrasting examples I showed you, in July 2019, approximately 42 million grams of dissolved material had passed through these solid data loggers. These solid data loggers measure every 15 to 30 minutes. March 2019, we had double that, 84 million grams of dissolved material. One 5-hour event that we analyzed data for has 4,000 pounds of dissolved material passed through. I'll show you how we measured that. So understanding that measurements are instantaneous, we assume linear change from one point of data to the next. We use the average of that time period. We multiply the TDS associated with this averages and produce the summation of results. So basically, since these bonus data loggers were measuring every 15 to 30 minutes, we took 900 seconds times our average TDS that we were getting in our recorded data. That was able to produce the summation of our road salt mass, basically. And that supported what we originally, or what I guess Dr. Farnsworth had originally mentioned to me, that she thinks that there's conductivity spikes, and road salt is actually affecting based off of that one event that we've seen, that it is strongly testing over time in many different years that it is. Talk about a little bit about future work regarding road salt impacts. Somebody could look into how it's affecting the ecology of these streams, and if it's overall affecting how much TDS is over time. If it's averaging at a higher set of dissolved solids, bringing pollen data longer around. And this is just some references, and I'd like to acknowledge Dr. Farnsworth for giving me the opportunity of doing this project and allowing me to learn and valuable skills with Excel and MATLAB and understanding how to read graphs correctly, really, and learning a little bit about hydrology. References that we use to get figures that I showed. So, yeah. Other than that, that's everything I have, and I appreciate you guys for listening and not judging me too hard. So. There you go.
Sodium salts. Various places they'll use ocean.
Yeah, I don't know specifically about that. All we did was just really analyze the data that was showing that Dr. Farnsworth already had previously, and we just corrected it. Other than that, I can't tell you, which salt is spiking up more, and which salt is actually affecting the stream more.
That was kind of the backhand way of getting it.
No, just what was in the data that we got to use.
Thanks.
Oh yeah, we had looked it up, but I didn't put the figures down. I didn't write the figures down. But other than that, it was approaching right around this. So like I said, this is one specific area. So I couldn't tell you right now exactly what I felt. So over the winter time, it had double times. It had to have been a lot. Like I said, it was probably in that one specific area. Wash away. For that night.
The road salt, your HCl.
HCl? Yeah, I don't know what kind of road salt it was, but I would imagine, whatever PennDOT's using. So I don't know about the ecology in these streams specifically, but I know that anything, like I said previously, anything above 230 milligrams per liter will affect drinking, and anything above 1,000 will start to affect the size. And graph that we have in here, has spiked up to 3,500 milligrams per liter in that one section. So if it's spiking 3,500 milligrams per liter, then it must be affecting whatever, like, I don't know what's running up. Maybe little minnows, but other than that, I'm not sure. I'm imagining it would be, though, especially if it's ever a 5-hour event, pushing out 4,000 pounds of salt, something's ingesting it. Also, just this one specifically, I'd say so. If we're seeing, like, it's maybe during some summer events, it was measuring around 200. I mean, there's more data that we have. We have highlighted. I didn't throw everything in here just because I was just trying to get the main point across that it actually is. Yeah. I would say so. I would say it's unsafe.
So here, I'll answer the question. Just much headwater stream. Find just a big spike.
All right.
Question from the internet.
Okay, yeah.
There way to determine if there's a growth.
Probably, I couldn't tell you though. Imagine.
You also got a good talk.
Thank you.
All right, we'll need to get ready to go on.
Great.
Thanks to the engineering department. All right, we'll continue with our next talk by Bennett Falvo on the geometry and kinematics of foliations and intact seafloor stratigraphic section in the north central range of Taiwan.
Thank you, Professor Coles. Morning, everybody. My name is Bennett Falvo. I'm a senior here at IUP. I've been working with Professor John Lewis for the last 3 years. And this is my proverbial slice of the pie. I'm doing based on the transition from subduction to exhumation, north central range of Taiwan. Got this keyboard here. So Taiwan is an island in the South Pacific off the coast of China, and it is an active arc continent collision where the Chinese passive margin is nothing to beat on the Arctic sloping moves north at roughly angle of 305 degrees. And it's causing a exceedingly fast exhumation rate. And so in the simplest of terms, and I love that box, it's right there in front of in a simple term, the Taiwanese mountain belt can be described in the probably virgin wedge model, which we can sea plate. What this sets up is a 2D model of the flow of material as it is operating. And it's a 3D
dotted line right here is 90 edge on this side in the beige and yellow here. Retro edge blue purple. So it is a generally pro edge and a retro edge through as being as organic.
So this is a 2D representation. So there are two types of obliquity that are affecting the deformation of the origin. That is roughly 5 degrees at 90. Regional trend of higher mountain range. Other one, urging geographic on art. So these two types of obliquity have not been accounted for in the doubly virgin ice model. These are movements of the first model is this right here, right? This is essentially that it was moving in, so just being zoomed upwards into the mountain range. You're seeing that it is also being reflected up to the left along the boundary there. This one in the second one in which it goes to a deeper level where it gets thermally weakened underneath the topographic side, and it is connected south uplift. So from this, we are viewing a stratigraphic section from the Mubo River in Taiwan, which is a percolated metabasalt, which has a inclined vein and interbed, probably still right below it. So why this thin section is important? Because it is a lot less deformed than the rocks. So we believe that we can gather more data from that. Is essentially where we're getting at. And you'll see that the rock around it is exceedingly highly deformed. There's lots of folds, lots of layers, kind of fold. It's just a little bit more taxing to gather that. Rocks around our stratigraphic section have foliations of varying orientations, most of which is S1 and S3 is a regional dip directions northwest regionally to the end. So from our stratigraphic section, we created thin section of our pebbly filling. Here is green filling. Here. So our green center sample lay two foliations. We have a layered parallel myelinated fabric and an overprinting cannulation cleavage, which we're calling S2. And what we see here is two section orientations. We have the northeast view up here, and this one you see across the section or across the sample essentially, where you can hold the shift. This is looking at a different orientation, looking down at the station. These dark, bold, black lines are essentially just cannulation for looking at it. We can gather some more data through that. And likewise, we made thin sections of light which show perfectly. This section also shows pattern. These probably light have a lot of levels. LS geometry, the maximum stretching direction, and optimum balance dip. This comes into play a little bit here as we'll see. So in the pebbly phyllite, there are strain fringes around the centimeter scale class, and these strain fringes indicate that they're both parallel to and perpendicular to the pebble long axis, suggesting that there's either a flattening deformation or multiple deformations that are occurring in the pebbly phyllite. So
from that, we can kind of conclude that the intersection lineation between S1 and S2, the intercalated slate and the greenstone, is not normal to or perpendicular to direction in the what we see here is the same granulations that we saw in the first thin section. Although kind of like here would be up here. We have this like approximately of section lineation between the S1 and 2, where the circulated slate almost in the direction of the class. What we can really kind of get from that, this suggests that the granulation is not coeval with the essentially with S2 younger than S. That opens the possibility that the same event that created S2 was what deformed the pebble. So that possibly is the transference at high angle, long axis likewise toward two events, which would have created S2. So just to kind of go over how I plot some of the data, I took an incremental measurement of all of the relations like this. I know the direct metric around 106. What we see is a couple interesting these peaks here, or as you get closer to the green, it kind of fucks the terrain. Like this is still it, but closer to the green. Here, here. We find is that the greenstone, which is a stronger material, kind of stuff. But on average, our apparent dip of the crenulation, and there's like 40 crenulations. So from that, we were able to derive a plane from the orientation of the thin section. So we had the northeast section with the crenulation cleavage that had looking along, looking down at northwest. And right of 43, 31. This falls into the regional S3. So what we've essentially done, our stratigraphic section, which is information event, all of the highly different rocks around it that have three deformations, which our S2 cleavage is oriented in a similar fashion. So essentially from this, we could do work with our better being less deformed, more strain analysis, taking more thin sections, and so on and so on. So just wanted to give a huge shout out to Professor Lewis. He has been so patient. Mentorship has been really appreciated. Full learner. So also Morgan Stat and Adams, who aren't here, they were Team Techno members. Involved in this. Here, working with Professor Lewis and other Team Techno members. Actually, one of them's in the cloud, Marshall. He's not in the PowerPoint, but I want to shout out her. So, and with that, any questions?
Data you've gotten so far, can you go back to those two bubbles and one of them more than the other?
I believe the one where the material is getting extruded out was what we're going with, but the data kind of points that either one can be correct. So it's kind of just like, I just ran with, for my poster talk, I just ran with that it was the top to the right. It was the water where it was going to the south. Sort of not on that. Could be wrong. I'm probably wrong, but that's fine.
then this earthquake that occurred recently into those.
Actually go back.
So which figure are you referring to, this one, right here?
Yes. Well, I'm actually not entirely sure.
Professor Lewis, what?
Last week, your mobile phone. 7.4 was to the R.
This scenario, just anywhere else besides.
Well, that I don't know, but I'm sure it probably does occur other places. I wanted the new kind of information that was in the study, but I'm sure that other questions?
I think the mechanism that is causing the
I believe that was the second day, and I believe that last half of rain that stratigraphic section upward. So I believe it kind of accurate that last what usually would have been S3, but in our section, that's after that. Or what the exact number was.
All right. Further questions? The thing is speaker again. All right, it's time for our next talk by Morgan Hoover. Analysis of reheated eruption samples from Oregon Cascade, Cinder volcanoes.
Anyone know a way to get rid of this bar down here? Probably going to obscure some of my nails.
Right.
Good morning, everyone. I'm Morgan Hoover, and my project is cross-analysis of reheated eruption samples from Oregon Cascade volcanoes. And my advisor was Dr. Nicholas Beardo. Well, you were my first choice. Well, I'm looking at very anomalous called microcrystalline inclusions. Now, these are inclusions that are found worldwide in low-intensity eruption volcanoes in both subaerial and submarine cinder cone volcanoes. Now, in Lake Flores, Lake go up as very dark within a larger and microlake form. In SEM imagery, we can actually get the crystallization texture much more obviously and describe them. Now, microcrystals. In comparison with this, we have this upper portion, which is the actual microcrystalline inclusion, characterized by very densely packed crystals with a wide range. Now, the mechanism behind this is really up for debate as for the creation of them. Now, the specific mechanism we're hypothesizing is volcanic reheating through recycling, which is visualized here in that red arrow. Now, typically with pyroclasts, have very short, slow trajectories that clear the entire volcanic vent, just end up, building up. Yeah. And occasionally, for vertical trajectories, it could allow for pyroclasts to fall back to the volcanic vent and experience additional heating. So, to create these contrasting textures, we would have a pyroclast initially erupt out of stone. We would have it re-enter, heat up additionally, and get entrained into juvenile. And so that newer juvenile melts would be the microlite portion, and the microcrystal would be stable, that would be once and then. Now, the specific experiments I'm looking at are repeating experiments from 3 different cinder cone volcanoes, 2 from the Oregon Cascades and 1 from New Mexico. And we're looking at natural test samples, and I'm performing a cross-analysis on this. Now, for these experiments, these are the following steps we typically go through. First, take samples, natural test samples, cut them in half of those an experimental and a control sample. Then we take the experimental samples, heat them in a cinder cone furnace, or a vertical tube furnace that recreates the environment of cinder cones. And we heat them at a specific time, a specific temperature within these 2 ranges. So the ranges are 5 to 66 minutes, and then 700 to 1,100. Once we have the samples experimented on or just applied, we're going to take them, embed them in epoxy resin in the tube. Then we take those tubes, cut them in half, break through the samples, and then we those tubes and then embed them again in groups of 3 to 4 in these epoxy cups and polishing tables. And then finally, polish the samples down to SEM quality, so they're actually decent quality. For my specific study, I'm looking at how silica content impacts these. As needed, I'm looking at 3 different cinder cone volcanoes, and they each vary in their silica content. Now, with this differing silica content, I want to see the effect of crystallization time and that silica has on these samples. Now, to characterize these, we're going by mineralogy and a framework of crystallization that was established by my advisor that he used in previous experiments that worked out for him, and he used various papers to create this framework. Now, mineralogy, in these SEM images, they are able to be identified by the color and the kind of shapes these crystals are forming. Now, for plagioclase crystals, tend to form as these elongated crystals that are very dark gray. And pyroxene crystals go up as these very short fuzzy crystals that are medium crystals. And then we have oxide colors that show up as these really bright white spots that are typically pure gold. Now, time to actually get into that framework. So, for the first type that we're looking at, we have 4 main types for the crystallization. And this is none. So basically, this just looks like what we would see in samples. So there's no visible new crystallization, and we really only see existing microlights that were already. have incipient crystallization, characterized by the sporadic beginning of crystal nucleation and phase separation of elements in this glassy matrix. We have alteration for about 1 to 5% of, and so phase separation of elements is visualized by this kind of blotchy pattern. Not the best image, but this is what we have. So we have dark and lighter spots that are still within the matrix. And what we're seeing here is certain elements becoming localized in the region of next, we have patch crystallization. So we see alteration to about 50%. You can have variation with that typical amount as well. So we have the original glassy matrix down, no real alteration there. But this upper region here, we're actually seeing some crystal alteration. Now, have the phase separation of elements crystals in here and crystal nucleation. But additionally, we're actually seeing identifiable crystals because they're actually finally large enough. With sporadic crystallization and incipient crystallization, we can't actually identify. For extensive crystallization, we have basically nothing left. So everything has been altered, and in the most extreme, I have 1 to 5. So this is just a comparison slide. All the extent crystallization types. Additionally, we have a legend here up in your left-hand corner, and this will be used for my graphs going forward, and so it's best to explain it here. So we have a gradient from white to about a medium gray, which shows how extensive crystallization. So none correlates with the light color, extensive. We have a graph. So these are standard graphs. They're a little complex to look at. So I'm going to walk you through a bit of them before we actually go into any of the depth. So right here along the y-axis, how long we reheated these parts. Then the x-axis has temperature that we reheated each day. You might notice that there's some shading in the background, and that represents the crystallization type right on the previous slide. And additionally, a point data set shows the mineralogy. Now, this bare box shows crystallization. This blotchy box shows phase separation. And then the final one is a bit more complex. So we have 4 windows, simple, and each dark spot represents a mineral. So here at the edge, we have all 3 minerals. Actually, here it's being oxide. Now, the specific data set we're looking at is the lowest composition set from our available data. And this is 28% silica. And this is from South Bachelor, Oregon. Now, for this data set, kind of patterns we're seeing very late onset of crystallization. So the onset of crystallization doesn't really occur until the later temperature, later. Additionally, minerals are really only identifiable at this high. Next, we have our medium composition, which is from South Shore, Oregon, and it's about 52 degrees. Now, this sample, in comparison to the previous data set, has much earlier crystallization onset in temperature and in time. So we are actually seeing variation. Additionally, actually see identifiable minerals at much lower temperatures. And lastly, we have the high silica composition. It's from Perth, Mexico, and it's at 55%. And with this, again, in comparison, much earlier onset. So before just being really this crystallization, right? So it's at around the same temperature, but the latter extent are moving down. gather from these caps. Here pictured on the left, the lowest silica composition and the highest silica, just for comparison's sake. So you see as silica increases going down, onset of crystallization at earlier recent years and earlier. Additionally, with these more evolved compositions, a wider array of minerals. That's my conclusion, and the sake of this presentation is for the amount of work I put in. I really want to thank the department for giving me this opportunity for research and providing funding. Additionally, I would really like to thank Dr. Nicholas Deardorff for being with me for this wild ride and providing advising. And lastly, I would like to thank my family and my fiance for providing me support. Thank you. Are there any questions?
Yeah, so the silicon content directly affects organization, or is there something else present in there that's causing that?
So this is more speculative than anything. We are pretty much thinking that silicon composition is probably more of a proxy for water content. So we find with big tech, for example, that the lower silica content has less water and thus less ability to. I think it might be more of a question. Silica provides us with the best.
Any instances either of the like there was an overgrowth of where we could have wrapped around it. This thing.
Yes, so we see with the some of the incipient crystallization, we are seeing purixines that start to grow along the edges of place crystals. But we don't really consider that too much with this because it takes much less energy for those to form, and so we focus more.
Is there some other constraint? Careful observation to help.
So Dr. Deardorff did some of his own experiments. The first ever experiments that we really did was with pyrrhotine. So we were facing this on his own observations. Additionally, we do have one other case. If I had the opportunity given to me, I would love to. I love mineralogy and I love the side of geology. So I would love to, but I don't have a graduate program here, so I don't know how far I would be able to. I could always go somewhere else to a master's project. You know, we do not have a very robust data set. Dr. Dorf honestly probably it maybe a new experiment. So there's not a lot of robust. Yeah. So that's definitely something that we need to take into consideration. But we just so most of the time, personally, would kind of calibrate our eyes to see like the typical like pattern crystals. Additionally, if you see something really funky, you want to look at your control. So we most of the time weren't looking at the, okay, so we have this experimental sample, what does it look like? So it's more of a last resort, just all of those visions, but first do this. So, to my understanding, it's the bones action series. We do see that lower silica samples are less evolved, typically have more oxide. Reflected portions.
To add to that, yes, start high, start down. Hasn't been a lot of experiments on this type of thing. Now, 700 degrees is thick. Typically, salt has flat. You don't get any diffusion at lower temperatures. As you warm it up, everything is saturated.
In the specific lab environment we're looking at. Oh, in the volcano, to my knowledge, it's around slightly
Higher.
higher than that.
More like 1100 to 1200 degrees. Eruption immediately starts. But as coming up through the conduit, it's higher end of that sort of top portion. Or maybe around higher something, then you get down.
That's in my knowledge with the data sets I've looked at and papers I've looked at, they're pretty rich both in marine and setting. We didn't really look at
That range. Still they're working on the Volcanoes, the eruptions. It's much more explosive. Like everything fell and carried as these really small little bursts. These little bursts that are bowling style eruptions chop things up and they fall right back.
Scattering, it's for having time to interrupt this wonderful. A couple of notes. We will, especially our notes to our friends online. And I want to thank Professor Farnsworth for engineering today. She's a broadcast engineer as well as her many other skills. So we will be breaking the online version until about 11:30 when we'll be back with another presentation. And meanwhile, everyone here can partake. I think we have some posters we've gotten hung up outside, so you can take a look at and discuss it.
You're doing the intro, so I just kind of forgot I was supposed to intro you. We need to get this up and share screen.
It's up.
Oh, you guys are good?
We are live.
Okay. All right. Well, I'm here to not introduce our next speaker, but to welcome you back from our poster session. Thank you all for kind of moseying around, chatting with the students. Our next speaker is going to be introduced by her previous research advisor. I apologize, but he begged to do this introduction. He says he limited it to 25 to 30 minutes, so you might want to grab a chair. But Dr. John Lewis is going to introduce our next speaker. Thank you, John.
Yeah, it's very funny. So it's super exciting for me to have the opportunity to introduce today Dr. Ellen Lamont. Ellen, I had the pleasure of having Ellen work in my lab as Team Tecto, as we call ourselves. Ellen came to IUP from after starting at Kent State, and came to IUP, and which is closer to home. Home is Crescent, which is famous or infamous maybe for whatever the weather is when you're driving 22. It'll be quite different when you're there.
That's the spot where the snow is.
Yeah, it's a very weird spot. I don't know if there's any influence on Ellen's character, but anyway, as soon as she arrived, immediately was involved with like every kind of organization and club and thing that was distracting that you can imagine. But
Spoken like a true research advisor. Spoken like a true research advisor.
Yeah. And but Ellen,
You want a chair?
I'm gonna need it.
I'm gonna be fast. So Ellen was just doing a lot of club stuff, community minded, and that's a very important theme. Ellen is interested in community and giving back to community and doing meaningful work. So right away, I was fortunate enough to be in a position to ask Ellen if she wanted to go to Taiwan to do some field work in Western Taiwan. Had some money from the National Science Foundation. So Ellen was the first of the students that I was able to bring to Taiwan over the years. And I remember in the field, being out in the field, there were lots of firsts, like a million firsts for Ellen in this experience going abroad. And many times incredibly engaged in as complicated as can be tectonic questions of Taiwan, but also sometimes looking incredibly perplexed, like what the heck am I doing? What is going on? And in spite of that, came back and she wrote a proposal to participate in a funded undergraduate fellowship program at Academia Sinica, which is like a national lab equivalent in Taipei. And it's competitive, it's international, and she got it. And then she went and spent the summer in Taiwan, and I detected a pretty big change occurred, and she returned, continued the work, gave a talk at GSA, Geological Society of America meeting in Pittsburgh, hitting home runs left and right. But it was a transition to, I think, a lifelong global learner who's really community minded. So she went to, after graduating in 2012, she went to UConn and worked with my PhD advisor on more work in Taiwan, broader footprint, bigger part of Taiwan, did a great job with her master's, then went to Oregon State to do a PhD with Andy Indermegs and that work in the Himalaya in India. Just, you might expect this, but she wrote a proposal, got a Fulbright to spend a year, funded year in India doing work that has meaning to the community, like trying to connect people into their understanding of their hazards and the place they live, which is really speaks to Ellen's values, I think. And so ended up doing that and ultimately getting a job at the Bureau of Reclamation after spending a little time in Colorado and Boulder. She'll tell you more, I'm sure, but emblematic. She did her PhD during the pandemic time. I was forming new relationships with some folks at Oregon State and other Sea Grant, NOAA-funded organizations and people, coastal and ocean people. One of them is Sarah Colasar, who I just got a chat snap face or whatever from a few minutes ago. So Sarah, I'm talking to Sarah in 2 dimensions in Zoom, and she's in Oregon State in a coastal ecology. I said, oh, I had a former student who's there. Her name is Ellen Lamont. And she said, oh, I know Ellen. She's like on banners all over campus. Like
That's true. That's true.
And so I'm thinking, well, that's Ellen. I'm not at all surprised by that situation. So it is an incredible honor for me to be able to welcome Dr. Ellen Lamont today to give this talk. So.
Thank you so much, John. I appreciate that. And he is right. My face is unfortunately plastered all over campus. I'm the face of OSG right now, which is amusing. And yes, living in Crescent did shape my kind of future. I chose that I told myself I would never live in a place that snowed ever again. And then I ended up in Denver, Colorado. Here we are. So it's really a great pleasure to be here to talk to all of you today. It sometimes blows my mind that I started here almost 20 years ago. It feels like yesterday. And so it's really great to be back here. And I think when I started, Katie was actually a brand new professor. So it's been some time, but I'm always really impressed when I come back here. And I haven't been back here as much as I would like, but when I do come, I'm always amazed at the work that the students that are here, what they produce. Really, as far as schools go, you guys are in a really great position because so many undergrads don't have the opportunities that you get here at IUP. You know, it makes you really competitive in the world and go forth and prosper. And I would say that's very true for the life path that I've taken. John, for me, has been the reason that I kind of became what I did and where I've gone in life. And when he talks about many firsts, like I was just a sheltered country kid who had never even left the Tri-County area. And here I was in an island on the other side of the world. And now I'm a globetrotter. A little bit about me. Sorry, I'll come back to this, but please, there's going to be a few slides where there's no photography, just as a side note. But a few things that you'll know about me is that I've now worked in 9 different countries throughout sort of the course of my degree period and then beyond. I have now worked in all 18 Western states with the Bureau of Reclamation. I've held jobs in private sector, academic, government, and for not-for-profits. So I've kind of been around the block, I think, at this point. And it all started here. So it's been a really great and wild ride. And lifelong learner. I'm still enrolled in school just because I can. So I'm at the University of Colorado Boulder doing an Earth Analytics degree or certificate rather in AI-based geosciences. Because this morning you heard that the face of technology is changing and the face of the science is changing, and I see it and it scares me. But it's also really exciting because there's some really great new things and new technologies and new tools out there to really do this work in a very different way. So just threw a few photos up here just to show that I'm a person of many hats. I work for the Bureau of Reclamation, which means that I work with dams. Most people here probably don't know what we do. We're a pretty quiet organization. When I took my job, I actually didn't know what we did. I'm learning every day. But actually, Bureau of Reclamation is a pretty incredible agency. And most of you may be familiar with this dam. Does anybody know what this is? It's Hoover. It's Hoover dams. So this is kind of our prodigal child of the dam world at Bureau of Reclamation, and power generation for LA, lakes going dry, that's going to be a problem, climate change and all that. But the Bureau of Reclamation, we're actually the largest wholesaler of water in the country. We provide water for 31 million people. That includes basically 1 in 5 farmers in sort of the entire country. Those farms are about 10 million acres of farmland that are irrigated by our water, which produces the vast majority of the fruits and vegetables that we produce here in the country. So we're, I think, a really, really integral part of sort of the economic success of our country. And it's always a challenge in the face of changing climate and aging infrastructure and discovery of new hazards as our science evolves. And so it's a really enriching job. We're also the 2nd largest producer of hydroelectric power, which LA is very thankful for. And I keep joking about the water levels, but it is actually a serious problem that we worry about, because as our water levels sort of change, if we can't produce the power, we can't, pump water for other power storage. We can't get things into our canals. We can't irrigate our farms, and we can't power our cities. We can't keep up with our other critical infrastructure if our dams aren't kind of working. So lots of moving parts in this field, in this industry, but it's a really interesting place to work. And so just throwing out there, we do cover the Western 18 states. We're broken down into 6 sort of regions. Each region is quasi self-managed within reclamation, and they kind of make sure that the safety function and kind of client interface is covered. But my job actually is not in any one of these regions. I actually work for the Technical Service Center. So we're essentially consultants within reclamation for reclamation. We do all of the technical science for all of the states. So I travel about 150 days a year into the field. So it's a pretty large chunk, but I do work. My work has lately been focused in Montana, Idaho, Colorado, California, and parts of New Mexico. But I have touched all of those states in some way, shape, or form in my time. So you might ask yourself, John said, I came from Team Tecto. I did this work in the Himalayas. I've done this work, in Germany and other parts of the Adriatic. And the question is like, how do you go from a tectonics person to working in water conveyance? Like, what a change. I asked myself that at first too. And actually, I can explain this to you through a story that actually might be familiar to many of you who are here and local. This is a depiction of one of the worst man-made disasters prior to 9/11 in the United States. And it's right here in our backyard. Does anybody know what event this is? Johnstown flood. This is the Johnstown flood. So the Johnstown flood actually is what got reclamation really focused on dam safety. It was not the final straw, but it was the start of the conversation that got us there. And for those of you who maybe aren't so local or don't like history very much, I'm just going to give you a history lesson anyway about the Johnstown flood and why it's really important. And so this is the Conemaugh Valley. And so the town of Johnstown is down here. And the Conemaugh River kind of flows up and around. There's several tributaries. And this bouncy little star over here represents the dam that eventually failed in the Johnstown flood. The Conemaugh Valley of the post-Civil War era was a bustling hub of economic activity. It was sort of the focus of growth for big giants of the time like Carnegie, Mellon, Frick, and many others. They really utilized the resources that were here, the coal, the timber, the steel, and the railroads kind of all went through this area. It was really a bustling time. And at that time, that population center was over 25,000 people. And, if you've been to Johnstown now, it's not quite the same, but it was really a big bustling hub at the kind of the turn of the century, late 1800s. That's a really big town. And so the unfortunate thing was that this looming hazard existed just up the stream with the South Fork Dam. And the dam itself was constructed in 1852. And the purpose of that dam was to sort of supply water to the Pennsylvania Canal system, which would then kind of help with all the industrial activity in that area and move it on. And so when they built this dam, it was 72 feet high, and it was made of like an earth fill. So basically it's a dam that's made up of a bunch of rubble and sand and silts just sort of compacted in a quasi-engineered kind of way to hold the water back. And so by the time they finished the construction on this dam, the canal and the railroad system that were here that this was designed for became obsolete almost overnight because private entities had actually developed better railroads and better systems for getting water to this area. And because it was obsolete, they were like, why are we going to continue maintaining this? And so they didn't. And it fell into disrepair, and within 10 years it had burst. But that burst was not the Johnstown flood. That was a small burst. So the dam was rendered kind of useless, and it's got this big hole in it, and it was left to sit there for another 10 years. 10 years later then, the land was purchased by a bunch of investors and entrepreneurs who wanted to form what was sort of an elite resort area. And when they formed that area, they wanted to rebuild the dam and, make it a place where, the rich could really have a good time, jolly time. And so This was a picture of the dam after they reconstructed it. The dotted line here represents the area of the dam that was burst in that original break. And so this is the area they filled. The original dam is below it. And behind it, you can see the lake and the clubhouse that belonged to the South Fork Fishing and Hunting Club. And, you know, this was such a disaster. Not because it was really a disaster, but like, what were they thinking when you look back? Because this was the perfect storm for a tragedy. Because number one, in this image, there's a culvert at the bottom of the dam. We love these when we build dams because this is our outlet work. This is the thing that allows the water to be drained pretty regularly outside of the reservoir. It maintains water levels. It maintains sort of stream health and habitat. It helps with recreation because that's how you keep the water moving. You know, you have downstream users that need it. When that first dam broke, that culvert broke and they never fixed it. So there's no way to drain the dam from the bottom. Problem number one. Problem number two. The dams always have a spillway for emergencies. They look like ramps if you've never really seen them. They probably make really fun skating parks if you want to have a death wish. But you know, they're designed so that when a reservoir reaches a certain capacity, it just sort of flows out and over. A couple of problems. One, when they decided to make this lake for their residents, they stocked it with fish, and they were afraid that the fish were going to escape out of the emergency chute. So they put up netting and barriers to keep the fish stocked in the lake. And it took a spillway that was designed to be able to pass a 100-year flood event, so a fairly large event, and it reduced its capacity to a 25-year flood event, which is a pretty common storm these days. So you don't have an outlet work, and you can't take an emergency spillway and use it effectively. Those are two problems. Problem number three, this area that they filled, like I said, there's a quasi sort of engineering component that goes to making dams. They just picked whatever rubble they could find and they stuffed it in the hole. This thing was leaking like crazy. And everything is slumping around. We call it internal erosion, when the materials kind of move around inside the dam from the water flow. And so this thing is nasty and it's not holding well. And when they made it, there's a little low spot right in the middle of it. And that little low spot, if in an overtopping event, that becomes a nip point. That's that spot where everything starts rapidly eroding when the water goes over. It's like a waterfall. So this is a really big problem. Finally, perfect storm. They decided they really wanted to make that 1-lane carriage road a 2-lane carriage road so they could pass each other without having to wait. Most normal people would take the dam, which is a triangle, and you just make it a little bit bigger. That makes the dam safer, more stable, it's wider, it's great. Oh, no. They said, let's cut it down to make it bigger that way. We'll just cut into the triangle. When they did that, they reduced the freeboard height. So basically, the distance between the crest of the dam and the top of the water. So you have a dam that can't hold back as much water, a dam that can't release water, and a dam that's falling apart. What could possibly go wrong? So unfortunately, in 1989, they had a 6.6-inch rain event, which was considered a 100-year flood event at the time in less than 24 hours. And the dam could not take it. And so 3 hours prior to the bursting of the dam tender that lived in this house saw the signs. And he was like, we are in trouble. This is going to fail. And they started communicating that downstream. But the problem is we're in 1889, 1890 times. Communication's slow. It's not effective. And this was a political nightmare. People were so angry that the rich and wealthy had their elitist resort. And they took everything related to news of this as misinformation and propaganda. So nobody heeded the warning. Nobody. So this dam actually burst in the middle of the day. And when that dam burst, half of the people were working and they were out of the area, but most of the people were in the town. And what made this such a tragedy and why it's one of the worst things that has happened is that it sent a wall of water 35 to 40 feet in height down this narrow valley towards Johnstown. Imagine, it's like a tsunami just racing down your valley and you don't know because you don't believe it. So unfortunately, when this hit the town, it decimated everything. 2,200 people were killed. Lots were injured in the process. And unfortunately, what made this particularly difficult was the fact that there was a viaduct, so a railroad train over the river system there, like this. And it caused a new dam to form when all that debris from all that damage got stuck behind it until the pressure and buildup of all that debris and all that water broke the viaduct, and it sent a second pulse of flood down the river again, past Johnstown. So basically you had 2 outburst floods, back to back, destroyed everything. And after the dam burst, everything caught on fire. So it was just really a horrible travesty. And this catastrophic disaster then really ignited passionate discussions about the importance of dam safety. And why did this happen? What could we do about it? Is there better ways to go about this? Should the government be overseeing the way we build our dams? Not just the federal, but all dams, because these impact everybody, right? Unfortunately, no real legislation was passed until 1977. It took another 60 years of these discussions and these horrific events and more dam failures before finally somebody said, enough, we're done. And that was the failure of the Teton Dam, which was one of our dams. And it failed immediately after construction. It was constructed, they filled it, and it failed. And it was so expensive. It's a multi-billion-dollar failure, caused so many loss of lives. And the government was like, we can't keep doing this. And to give you an idea of how common is a dam failure, this is a graph of number of dam failures through time. It's not 1, it's not 2, it's thousands. Since this record has started in the kind of the mid-1800s, almost 3,300 dams have failed. 3,300. This area in orange here represents the time when the law was passed to start thinking about dam safety in a real way. Look at the number of failures it took to get there. But we did it in the nick of time, because look at the spike. The spike has nothing to do with the fact that we weren't now approaching dam safety, and more with the fact that our dams have a life expectancy of 50 years, and our average dam today is 75 to 150 years old. So what do? You have dams that are old, they're deteriorating. You've got a water heater. Your water heater has a life expectancy of 20, 30 years. Sure, it'll keep running afterwards. But then when it dies, then what? Or how much you have to service it until, same thing with dams. You really have to service these things and maintain them and have plans in place if the unfortunate happens, right? And so, long antidote to say, how did a structural geologist get into water? So I'm in this job because when we discuss dam safety isn't just about the water in the downstream population. It's key, it's important. We care about life loss, it matters. But how do the dams fail? They can fail statically, which is they have a problem with the dam itself, the integrity of the dam. But they can also fail by triggering. In the case of the Johnstown flood, it was a flood event. It is a big rain event that flooded it out. But there's also seismic concerns. What happens if you have an earthquake? Is that dam gonna stand? So where I come in is more on the seismic side. I work with our engineers and our ecologists and biologists and all the bureaucrats and lawyers to eventually get to a point where we can assess kind of what is the safety and risk of our infrastructure. But I do that from that seismic tectonic side. So I want to actually cover then what is risk and how do we think about risk when we do this type of work. And so for us, we break down risk into a few categories. And the reason that we want to assess this risk is because we want to make sure that we have built resilience. We want to make sure our communities are resilient, that our dams are resilient, and that our plans are resilient. We do it because we want to make sure that we can recover pretty quickly. We want those capacities built. We want to make sure that our communities are prepared for like emergency preparedness. And we want to get better about communicating with our public when we think about risk, because they should know the risks that they have kind of posed to them, but they also should know that they shouldn't ignore warnings because they think it's false news. What does it mean to have a real warning, and what does that look like, and what do you do about it? And so the risk system that we make, like all government things, has an acronym, RIDM, which is Risk Informed Decision Management. Essentially what that is a fancy way of saying we assess the risk and we put the resources towards the biggest threat. Because we don't have infinite money to fix every dam that has a problem, but some of our dams have more problems than others that really are a concern. And so the areas that we focus on then are hazards, performance, and consequences. For hazards, you can kind of think of the hazards as the triggering event. So is it floods? Is it earthquakes? Is it liquefaction at the dam's foundation? So we ask them, what are the hazards? How often and how severe are those hazards? And what are the conditions at the dam that kind of are in play when you have a triggering event? You know, what's the foundation made out of? What's the dam itself made out of? Is it concrete? Is it rubble, embankment? Then with that information about the triggerings, we look at the performance, which is essentially the dam efficiencies. So is there a problem with the dam or not? Is it a static problem or is it a triggered problem? And so when we do this phase, we want to know, how is our dam going to respond? Is the performance satisfactory under that response? And this is something that's more the engineering side. Stay away from that. But it's something that's, you know, you put it in a finite element model and you kind of model what that dam response would be to the triggering events, or if it's static, to the conditions at the dam. And then finally, the most important part is we assess the consequences. And these are about the magnitudes. So how much loss of life? How much economic impact? What is the population at risk down from the dam? And so we want to know all of these things, and they all get put together into what becomes a risk assessment or risk analysis. And that's how we move forward with kind of fixing our dams. A great example of a challenge, and actually make sure I said what I wanted to say. Yeah. So one problem with the risk, and one thing that kind of contributes to the risk, is that one is the state of deterioration. I already mentioned of our dams, they're getting old. So that's a problem that we have to think about with risk. The second one is a changing climate. So yes, maybe we're getting less rain regularly, but we're getting bigger storm events. And when those events happen, that becomes a triggering event. And so even if we are holding less water overall in our reservoirs, we could fill up like that. And it's not uncommon in places like California. Shasta reservoir for the dam out there, it thing constantly fills. It'll be completely bone dry. They're like, we're going to take 10 years to fill this. One event, it's full. That's a really scary thought, because what if you have two of those back to back? Then what? And then the last one is the fact that population centers downstream of these facilities are increasing. Even with COVID, people migrating out of the cities, they're still in the path of the potential flood that would happen if a dam fails. And that's just a fact. That's almost all the cities. And most of the dams are near cities. Many are also in the middle of nowhere for other reasons. But we have some really serious dams near really big population centers that just keep getting bigger and bigger and bigger and bigger. And that drives up the hazard. And so getting back to the slide that I kind of skipped out on, is that Salt Lake City is a really great example of a place I would never buy a home. This place is incredible. Enjoy the eye candy. It's so beautiful. But it's terrifying to me working in this field, because with that beautiful scenery comes a really big problem. This is the state of Utah. Utah has 700 dams. 200 of those, shown in red as dots here, are considered high risk, high hazard dams. If you'll notice up here, that area on the map is Salt Lake City, Great Salt Lake. Notice that the highest density of dams is around Salt Lake City. And that's because you can't drink the dam or anything in Salt Lake, it's salt. So you need fresh water, you need irrigation water, you need something for your homes. And you'll notice right away that the population of Salt Lake City keeps increasing. Since the 1900s, 4 times the size. So it's grown immensely. Don't know post-COVID kind of what that looks like, but I imagine it's probably not that much different. A lot of people move there for skiing, if nothing else. And so this is a city that's really concerning because it's just surrounded by these high-risk areas, high-risk dams. And so part of the reason these are high risk, the Wasatch Fault. The Wasatch Fault is probably the most active intraplate fault in the United States. It's highly well studied. The USGS, the Utah Survey, Bureau of Reclamation, we have done so many studies to try to understand what's going on in the Wasatch. Because you saw those mountains, they're huge. They have big fronts. They have shorelines from Lake Bonneville that are just offset, deformed. It's a really scary place. It's very active. And most of those dams either sit on the fault or very, very close. And so this is an area that really is at risk, and we are concerned about it. And an example of that I want to point out to you is a dam I recently worked on called A.B. Watkins Dam. It's near the town of Ogden, kind of north of Salt Lake City proper. The dam is this really crazy polygon shape. It's a three-sided dam. There's not very many like it in our inventory. But you'll notice that the backside of it sits practically on top of the fault. This is a normal fault that basically dips under the lake. So it's extending, it's making the Salt Lake bigger, meaning that the backside of this dam is being dropped down when there's an earthquake. So one of the things that we often have to think about with dams like this is overtopping. So if you drop, this is the dam, if you drop the backside of this down, you're going to basically create what we call a seiche wave, a little tsunami from an overtopping event. You can get these in other ways too, but this is one way to get it. And so this is an inundation study we did to try to understand how much of an impact on the evacuation infrastructure this was going to cause if this happened. Because if anybody's been through here, there's a mega highway north-south that runs through here. There is like 5 railroads. There's a couple of other emergency escape corridors, a bunch of bridges right there. And so we did a flood analysis there to try to see, what would the impact be? What's the risk? Because those factors about damage to that infrastructure also goes into our risk assessment. Because if we have cut off the evacuation routes, we need to know that. So this is just an example of the type of thing that we might work on. And so, okay, so I'm still good on time. So again, my aspect of coming at this is about risk from the seismic hazard perspective. Basically what I'm going to show you from here on forward is a whole lot less data, lots of pretty pictures, because the work I'm going to show you is stuff that I'm actively working on. I don't necessarily have results from yet, but just to kind of give you a flavor of kind of what it is that I do. And so when we do these hazard studies, they're really done in kind of multiple steps or phases. The first stage, like any geologist, is reconnaissance. So you do a literature review. You do collect all of the types of imagery that are available to you. You may be looking at anything from parcels to be able to get land access, to zoning laws, to topography, to water drainage networks. We do work with paleo flood studies in our group, so you might be looking at those type of things. And then we ultimately are building a really solid map. And we're doing a lot of mapping because we want to know where are faults located that might be of concern. And it's really mind-boggling. If you've never played with LiDAR, please play with LiDAR. It's absolutely incredible. But LiDAR has revolutionized and also given me a very large pile of work, because there are so many features that you didn't know existed out there until LiDAR came. If you don't know what LiDAR is, it's high resolution imagery. It's meter to even sub-meter in some cases. You can get really high resolution images, and the LiDAR basically is a type of imagery that allows you to strip off the vegetation and just see the earth kind of bare and raw. And for my work, it's really important because I'm interested in deformation in the Quaternary. So really young stuff. If you have an earthquake event, you're looking in the Quaternary, 1, maybe 2 earthquake events. That's like a 1 to 4 meter scarp. If you're using 10 meter LiDAR or imagery, DEMs, you'll never see that. You need the LiDAR to see displacements in the 1 to 4 meter range. Okay, so we have all of this beautiful, rich LiDAR coming out. So we spend a whole lot of time just mapping in the office. And then we go out into the field and we field verify. And then we decide if we need to do more work, if things really look concerning. One example of what I might be doing with this is a place I'm working in Colorado, near a place called Rifle Gap Inn. You can see in this LiDAR, and it's kind of faded out. I'm sorry if it doesn't come through on the screen very well, but you can see the bedding. It's fairly vertical coming through this feature. This is the Grand Hogback monocline. There are lots of these really beautiful pediment surfaces that are coming off the monocline into the valleys. And we started mapping just the drainage offsets in the LiDAR. And there are thousands of little drainage offsets along this thing. This is a bedding parallel fault that nobody had recognized until they started looking at the LiDAR and went, holy cow, look at these. These like things end here, these drainages are offset, look at all these little, you would never have seen that without the LiDAR. And even in the field, sometimes it's really hard to see because again, you have to train your eye to offsets that are like, this to, this. So it's really hard to see. And so this would be the kind of thing that we would start with. Next, we go into a phase of seismic source characterization. Essentially, it's a really fancy way of just saying, we want to know the geometry of the fault, how often it ruptures, and at what rate. So we're characterizing it. We can do this many, many different ways, but very commonly in our group, the easiest way to get to that data quickly is we do paleoseismic trenching, which basically means I spend a lot of time with a shovel and a broom and a little brush. And I feel like I'm an archaeologist, but I'm not. Just to clean off the walls of the hole that we dug. And we sometimes get backhoes too. And what we're looking for is basically, if we do that trench across the fault, we're looking for the things that are offset. We're also looking for things that we can date to try to constrain when did that offset actually occur. And that's really fun. And I'm going to show some slides from some work I just did in Montana, some really beautiful results. But once we have that data compiled, what do we do with it? So great, you know the fault's active, you found the fault, you got some dates and rates on it, cool. How is that used? Well, we then run seismic hazard models. You may have, maybe not, have heard the term probabilistic seismic hazard analysis, a PSHA, PSHA. We run these very frequently. And the idea is that you have a bunch of input seismic sources. Those could be background earthquakes that are lower magnitude, or they could be faults that maybe are associated with big earthquakes, or just faults that we don't have any seismic history on. And we have rates that can be calculated and probabilities associated with those. And all of those things kind of get modeled together to be like, how seismically active is a region? And then if we have a dam, we say, okay, we have this idea of how active it may be. We have all these rates. If I'm at my dam, what kind of horizontal acceleration is my dam going to experience in an event? Okay. And so what the results of those are essentially a graph that looks like this. It's kind of ugly. But it basically shows the cumulative seismic hazard from seismicity, all faults, and then individual fault inputs for each. So you can kind of get a sense for how much acceleration is contributed by each of those sources. And then you can take kind of the time, the return period, so to speak, that these events may happen, and you say, how much acceleration? These then become the input models parameters to the engineering models at the sites. Okay? So we're kind of like the first order data. We're the real on the ground data that's going to the engineers to actually do the risk assessment. This dam was particularly fun. That picture I showed you with all the cool offsets of the drainages. So that's what this particular analysis was from. And I think my client kind of had a heart attack because we essentially said, you're going to have a peak horizontal ground acceleration in a 10,000 year return period of almost 1 G and almost 2 Gs in 100 to 50,000 year return periods. So basically, you need like 3 to 4 Gs to launch a rocket into space. So the engineers were very concerned. They were like, this dam has no hope. It has a static liquefaction problem, meaning that at any time, if there's enough moisture, the dam can just slide off its foundations because it can liquefy. Now you add almost 1 to 2 Gs of acceleration to it, and you have a big problem. So this is a dam that's been rocketed to what we call DISPER 1, which is kind of like our highest emergency level to do some work on. So sometimes we get things like this, but most of the time they're not this bad. And this feels a little bit like Taiwan level scary versus like, you know, Colorado Plateau. All right. So how much time do I've got left?
12:10.
Okay, so 10 minutes. Okay. So this is great. So I'm going to actually give you an example of a project that I'm working on currently in Montana. Like I said, I have projects all over the place, but I thought this one had a lot of really great photos. So I thought I could give you a sense for what I'm working on. And this is an example from the Bitterroot Fault in kind of the western edge of Montana, almost to the Idaho border. Idaho's just south of here. And as you can see, beautifully highlighted on the image here, this red line represents one trace of the Bitterroot Fault. This
It's amazing it doesn't go through the reservoir.
How do you range
goes
that?
through the dam too. Turns out, quote, 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 haha, the fault actually comes here too. So you'd be amazed. So it took me a little while to realize when I started this job that it makes sense that so many of our dams are located on faults. And it took me a moment, but I was like, oh, faults make constrictions. Where do we build dams? In constrictions. So, you know, it doesn't surprise me. This particular dam, though, is a little bit more unique. This was not necessarily built on a constriction. This actually was built to expand upon an existing glacial lake. So there was a paleoglacial lake that I actually think might have even been a bull lake, so second glaciation, big glaciation back. That they were like, this has already great storage capacity, let's make it bigger. And so they built it, and this arbitrary spot they decided to build it was right on Falvo Fault. And so they're really interested in this dam, partly because it is a fairly well-constructed dam, but it's the fact that we have pretty compelling evidence that there has been 2 to 4 earthquakes, Quaternary, maybe even Holocene, on this fault that has produced an offset scarp of anywhere between 4 and 10 meters. So you go, oh, one event, let's assume, is 2 meters displacement. Can the dam still stand if you offset it 2 meters? Maybe. I mean, in Taiwan, they had the Chi-Chi earthquake and it went right through the dam and that dam survived. It's possible, but they have to model it, right? And so they basically sent me out here to work on characterizing the Bitterroot Fault. This fault is fairly new. It was only really discovered in 2019, I believe, when the first set of LiDAR got released for the south half of the Bitterroot Valley. For those people who don't know exactly where the Bitterroot Valley is, this is a picture of western Montana. All of the red lines represent known quaternary faults sort of in western Montana. So these are faults that are quote unquote active. The Bitterroot Valley is here, so south of Missoula. It's a really beautiful hidden gem. If you ever want to escape somewhere where there's no humans, but it's the most beautiful place ever, go there. And so Como Lake is sort of at the southern end of this valley, south of Hamilton. And this area is one of the more seismically active areas, also from an earthquake perspective. This map down here in kind of tiny shapes shows, so here's like Yellowstone right in here. There's like the Yellowstone, but then there's this huge band of background seismicity called the Intermountain Seismic Zone. So it's an area that has a lot of energy already. You know, lots of things are moving, things are excited, you know, and you add all these faults in and, you know, you go, well, what's going on up here? Like, you don't see this in other places. This area has also had a history of quite a few large damaging earthquakes, most of them in the mid-3s, but some bigger, like the Hebgen Lake, which is in Yellowstone. And so, you know, it is concerning. And the reason it's extra concerning is that Missoula is the second most populous city in Montana. And it's a growing population, and it's rapidly growing. And none of the infrastructure there is prepared for an earthquake because they never knew there was a fault there. But the fault, we think, we're not sure yet, we're waiting for the new LiDAR, may even go through Missoula and join the 9 Mile Fault. May take a jog. So we're waiting for that data to kind of confirm that, but it could potentially be a very large fault. And if you learn about faults, you learn that there are scaling relationships that say the longer the fault, the bigger the earthquake. So knowing how long that is really important. But currently, we estimate that that could probably accommodate like a low to mid 7 earthquake. So it could be substantial. So all that said, the Bitterroot geometry is pretty complex. Missoula is at the top, Connor's down here. Here's Lake Como that we were just looking at. It's not like your normal type of fault in the sense that there are sort of two faults here that are a little bit complex. This is a picture of the mountain range front. And I don't know if this excites John or it should, but the face of that mountain, you see it's really flat and linear. That's actually a detachment surface from an older Eocene age fault. So the orange area essentially is the mountain range here. And that where it says Bitterroot detachment, that's the old fault. And it comes down below this tan area. And it's a big, big old fault that just makes that beautiful mountain front. And the Bitterroot fault, not the detachment that we're studying, actually, we believe cross-cuts it or maybe even soles into it. It's hard to tell. You really need seismic. We're working on getting seismic for that. But it has a really complicated sort of history. But we think that the Bitterroot fault system is a fairly young fault system. And the reason for that is when you look along the trace, and you'll see this in the next couple of slides, it's not one very clear fault string. It's like a series of, jumping around, offset somewhat in echelon, like subsegments. So it's disorganized, meaning that it may actually be a fairly young and developing fault system at this point. But it's accommodating a lot of deformation. So this is a zoom in. Sorry, let me back up and point that out. This is a zoom in of this little box right here. Speed it up because I'm running out of time here. But so this is the new LiDAR that was flown. This is the interpretation of the LiDAR and then the mapping from the LiDAR. And you'll be able to point out pretty quickly, there are these lineaments all through here. And then my favorite one, way up here, this lineament up here on the fan, there are scarps through modern drainage. So this is a really cool thing because what we found in early mapping in this area was that we have Bull Lake moraines that are cut. We have Pinedale moraines that are cut. We have outwash fans. We have shorelines from Paleo Lake Missoula that are cut. We have modern drainages that are cut. We have multiple potentially events because the magnitude of the scarps changes through time. The more recent they are, the smaller they are. The older they are, they're bigger. So we know we're capturing multiple earthquake events on this thing through the Quaternary. This is really exciting. It's really hard to find this, and none of my other faults are this good. So we work in areas that are crummy, but this area is great. I won't spend too much more time because I know I'm running out of time, but there are areas here on the map, like there are green dots here and then green dots up in that box where we've done cosmogenic nuclides to look at the moraines, to figure out ages, to make sure they were actually Bull Lake and Pinedale ages. And we've confirmed that, and we've done some very rough assessments looking at just displacement on across the scarps. And like where we were getting rates somewhere in the 0.2, 0.1 millimeter per year, which for the US is really fast. I mean, it's not California fast, but like we're in the middle of the continent, and so these are pretty sizable rates just based off of the offset across the surface. That's not actually doing any of the paleoseismic work. And so just sort of quickly zooming in again, just so you can see it a little bit better. You can see there are multiple multiple traces of faults along all these different surfaces. And that's that kind of disorganized sort of nastomosing, an echelon series of faults. But they cut through so many different units. It's pretty incredible. This is a published map by the Montana Survey. You can find this. It was released last year. It's a really, really cool area to look at. Speeding along a little bit though. So in an area kind of in the mid-valley where that triangle is in that picture, we did do one of, I think, 5 paleoseismic trenches along scarps along here. So this is the site. There's like an old mining disturbance and then off, and there's this beautiful fan right in here. And there's a scarp that runs sort of right off the edge of the fan. It does not cut through this modern drainage, but it does cross the kind of that surface. And so that little yellow box represents the area where we actually did the trench work. This was for our permitting purposes. And you can see in this one, the cross section across that scarp produces basically a 5.6 foot, why we did it in feet, displacement. It's 1.7 meters kind of across that surface. And so we did, oops, too far. We did go out. This is what the scarp looks like on the ground. I wish I had a person in here for scale, but you know, that is, like I said, 1.7 meters. Might even be a little more in this particular spot, but that's the scarp. And so we had our excavator come in and dig our hole for us. And you can see it's this really gnarly boulder stuff. This is not fun to dig through. And then eventually though, we got really excited because we found lake deposits, and we found also what looks like maybe river deposits that have like ripples and some cross beds in it too. So a whole series of stuff. But it's weird because its location relative to Lake Missoula, which would have been the older lake, is above Lake Missoula. So why is there a lake here? Its geometry actually looked like a sag pond, which is like a pond that sort of forms in front of a fault, but you don't often see that on normal faults. So it's kind of a weird thing to find, but they're pretty extensive packages of lake and sand deposits, and they get quite big, and they have sand lenses through them. And we also found Mazama ash. So we have a pretty good age marker, and we know that this Mazama ash is offset. We were able to find it across the fault, and so we know that's about 7,000 years ago, at least, when we found that. And these are the holes where we did OSL tubes for dating of the different deposits. So really cool stuff. And ultimately, this is the trench logs that we produce when we dig these holes. We did them in detail, usually by hand, and then we digitize them. And so the areas in blue are those sort of lacustrine style deposits, a little bit of the fluvial deposits. Then you have this really big, beautiful debris fan in Unit 6 there. In the middle that looks like it may have been a progradational deposit because it goes from really coarse on the backside and it fines until it goes back to the lake deposits. There's some weird deformation in Unit 7 that we're not sure that it's tectonic, but you know, the laminar layers are kind of peeled up, and I don't know if that debris flow maybe peeled up some of the existing one or what, but some strange deformation there. But the area in number 4, the orange, represents a earthquake generated colluvial wedge. So basically when you make a scarp, the material falls off the scarp and into a pile. And so we were able to get some dates from that, and it beautifully came back twice as 14,000 years in the OSL. So we know we have one event that took it through the Mazama, and then potentially another event at 14. So we can get recurrence intervals from that. Just some more really beautiful photos. Found these really cool drop stones in those lake deposits because we think that the lake that was there was sometimes covered by ice. So there's some really neat features through there. Kind of quickly get to the end of this. So yeah, just to show, so this was the boundary of the Paleo Lake. And then this is the sort of the modern Lake Como. And when the water is really low in the summer or in the winter, I mean, you can see sort of the boundaries of the Paleo Lake. And I was literally in the field like right before I got here for this part, but we did a chirp survey a couple months ago off the side of our boat to kind of look at the layers sort of at the upper part of the lake. And what we got back was something that looked a little bit like this. These are all the lines that we ran, the chirp. This is the imagery, and this is one example. I have way better examples that I wasn't allowed to show closer to the dam that we can see what we think to be almost 5 full events preserved in the lake. There are places where you have layers that are formed through here. There are some structures that the lady we're working with at the Forest Service believes may be dewatering structures in some of this. We do have an unconformity that looks pretty like going through here, like it eroded off some stuff, but the blue represents the boundary between deformed and undeformed packages. So we're able to really do some cool interpretations with chirp, which resulted in us on this trip going out to do some coring. We were gonna go look for some basically disturbance deposits, turbidite deposits. So this is my crew. We went out on a boat with a really cool rig on it. It's like basically on a crane, and it's a vibrocore, and it shakes as it goes down. And this is a pontoon we built to do some Livingston coring as well. This was the lake. What a horrible place to work. It's terrible. I will say we had a blizzard the second day we were there. It was miserable, but it was great the rest of the time. So that's our rig. We were able to break records for the guy who owns this ship. We got 15-foot cores, which was pretty great. And when we brought them back, they look like this. Any Dune fans? This is a core catcher. They keep the sediment in the. It's like a snake. But yeah, so that's our cores. And when we cut them open in the field for funsies, we were able to see. This is Mazama Ash. That is Mazama Ash. This is Glacier Peak, which is another 14,000-year-old volcanic event in the area. And so we captured some really cool horizons for dating. We're going to take these back to do CT scanning to kind of look at sediment grain size distributions and go from there. That takes me to time. So I'm just going to end here and put in a plug for anybody who's interested in government jobs as a student. This is a really great website to go to, and I'm happy to talk about it later if you'd like, if you're interested in kind of what we do. But thanks for your time. Yeah.
This is really terrific.
Thanks.
Not only just to have you back home, but to hear what you've been doing, and also feel a lot better about the concerns about salt in creeks.
Yeah, it's hard to sleep at night sometimes. No.
So I guess the question I have for you is that I know you're focused on the seismic part of the risk assessment, the flooding events from climate change. I don't know how well they're known, but and it may differ depending on where you are, and I don't know how well we model the hydrography of climate change in that area, but where would you put that balance? Do we even worry about climate change in this, or do we worry about the seismic? Because it seems like seismics win.
Euphemistically or realistically? We are concerned. But I will say that as an organization, we are in the infancy of trying to understand how we need to think about climate change. We know it's a problem. We have issues at our reservoirs that we know are related to climate. How to track what that looks like and what that means for the future is very tricky. We do spend a lot of time doing paleo flood studies, which is great for the past, but with our changing climate, how applicable those paleo floods are to our new kind of now, it's really hard to tell. So we have people thinking about it. Are we implementing it? Probably not as much as we should.
I have a follow-up question really from Steve's. With the larger storms that we're expecting that we'll get, how much do you guys model the effect of the water pressure on the rocks along the sides of these reservoirs? Because haven't we had failures from landslides slipping down in?
We do. Those are seiche waves. And so that's actually one of the failure triggering modes that we look at a lot is seiche wave. Especially if we have an area where we know we have a problem. Like we have a dam in central Colorado called Ridgeway. It's on a landslide, a mega landslide that's moving at like 5 centimeters a year. We know it. It's on the abutment of the dam. And so those type of things we look at and we're like, is this a concern? Do we have an issue with overtopping? And a lot of times the way we mitigate that from the get-go is if we think we have an issue, they drop the reservoir level. And so we have enough freeboard to catch the water from a seiche wave. But that's like a kind of if we have to. But yeah.
First of all, who forgot their field scale, and therefore had to use the hotel key?
It makes the most amazing core scraper. It's really, and it worked in my door afterwards.
Anyway, my real question is getting at, it's sort of addressing this too much water versus seismic hazard kind of issue. And you just actually sort of answered it with is the too much water mostly handled through control of water releases versus, worrying as much about dam failure? Is it more in the operation of the dam?
Water release is a really tricky topic because,
especially in the West.
Yeah, because you have, in addition to just the needs for safety, you also have water user rights, and water law is really complicated out West. And you also have habitat issues and water that can be maybe too hot and we have to release more than we want to. I mean, there's lots of factors that go into the release part. But if they think that there is a concern that could cause dam failure, they will always drop the water regardless of what the problem is. We actually have dams I think they're in Kansas, they're actually completely empty. Like the Republic River, we've got several dams on that are just empty because the dams are good, but the water right issue, they just don't have water.
I was going to ask you a similar question. So how many layers of bureaucracy, if you think it's going to be a failure, you and your team, how many layers of bureaucracy do you have to go up before they say, yeah, lower the dam?
It really depends. So to give you a perspective, it could be 10 years before a dam reaches modification point in our process.
Wow.
So my work often is a 2 to 3 year process for any one study. Then that data goes to the modeler. We don't know if we have a problem until the data goes to a modeler. So sometimes you could have a dam that's sitting 5 years between different investigations before you know that you have a problem. Then it can be immediate. They can go, holy cow, no matter how we model this is an issue, we need to drop the level, and they'll immediately drop it. Then they'll do more work. But until we get to that point, it could be a long time. Yeah.
I have a question about resources. So it sounds like if you have a project that's got the green light, I assume you don't have infinite number of dollars to go and do OSL dating and beryllium 10 and all the things. But what is you do have the ability to go and say, we need dates for these things. Is that all done in-house, like just internal proposal writing of sorts?
The reason I love my job is I don't write a single proposal. We are a $1 billion annual budget organization. We don't have money issues when it comes to if we need to do something.
So if you need OSL dates
So we have an in-house OSL.
Okay.
Shannon Mahan at the USGS, we bought her machine. So all of our work is for free. Cosmo is a little different. We have to work on Cosmo, but so we have some partnerships that help with that. But like if we make a case to our dam safety office that there's a reason this needs done and this is why, they give us the money.
It's much like around now here, so.
Totally. But I will say, for anybody interested, we do partner with universities a lot. So if you need to have a project that's relevant to us, we can probably work something out. We work with a lot of schools.
I'm wondering about doing this in the east. 40 years ago when I was a grad student, it was either 83 or 84, we had a magnitude 4.5 earthquake in the Adirondacks.
Mm-hmm.
And I won't mention any names, but I saw it was a little private dam built during World War I by one of the logging companies to make a lake to float logs. And this thing had a classic slump failure.
Yeah.
And it took it down quite a bit. And the seismologists I was working with wanted to figure out, they could tell from the seismicity, it looked like the earthquakes lined up along one of those northeast trending lakes in the Adirondacks. But, there's if you're not talking about the Ramapo Fault in New Jersey, it's hard to know where to trench, for example, for failure seismic. They did wait for the lake to freeze over and they ran GPS across, see if they could see an offset, didn't see anything.
Yeah.
And maybe there aren't as many facilities that reclamation has to worry about in the east, although I guess there's some. I wonder, you're lucky to have, scarps you can finance on it.
Most of the time we don't.
Those issues too?
So the east is the territory of the Army Corps.
Yeah.
And it's because most of your dams here out east are flood control. And we don't do flood control. We do drinking water and irrigation. So they actually have a whole team that does seismic stuff. And so, I think they employ a lot more like GPR or shallow geophysical techniques to find their features. And I think most of the time, even if they find faults, the slip rates are so low out there or out here that mostly it's controlled by background seismicity. And so they tend to model these places like New Madrid or like the seismic zone in other places and use that as their model basis. So faults are just not as important.
Yeah, but it's tricky because remember I think it was 85 earthquake in Kentucky.
Mm-hmm.
And before that, the seismic hazard map of the U.S., Kentucky was the lowest level.
Yeah.
They redid the map, some heads rolled at the USGS and it jumped up a few levels.
Yeah.
Do we really, is 90 years really enough of a background to know?
It absolutely isn't. And that's a problem that we run into when we're working with the engineers. That's my favorite part of my job. And, the question is always, does our data actually mean anything? Like, do our numbers actually mean anything? Because it's not uncommon for things to change drastically in 10 years. A great example of this is we often use the data that comes out of the National Seismic Hazard Model. Depending on what ground motion equations they use and in what areas and where those boundaries are, our numbers can triple or they can half. And so the engineers are often like, why don't you know this? We're like, well, Earth is hard. Earth is really hard. Like it's not just a model that we can throw it in. Like this is the reality of our data, and it isn't enough. We keep finding new things. I mean, just like this Montana example, like we didn't know about this fault 5 years ago. So we work with the best of what we have, and when new data comes, we model it again. Yeah.
It's sort of a story, but I had a house in Houston, and we had 52-inch rain.
Yeah. Wow.
And the water didn't come, it just came to the street, but not over the curb. Well, the Corps controls 3 reservoirs north of Houston. And the water was backing up and backing up. In the middle of the night, without any announcement, they opened the floodgates wide. 13,000 houses got flooded, including mine. And it turns out the Corps colonel said they just didn't believe it was going to rain 52 inches, even though every weatherman in the world, and you stood outside and you got wet.
Right.
So, they changed all the regs and the whole 9 yards, but it's this climate change thing with these severe storms.
It's real.
It's not a theory, and I guess this guy just decided on his own volition that they can't be right.
Right.
And the only good news was it was a flash flood, so it came and it went.
Yeah.
It does all the damage, but it doesn't sit there. But yeah, it was literally, by his own mission, literally not believing these big events would occur.
It's a real problem. And we even see that with our own dams out west in California. We've had quite a few times where we've had to flood out communities because you have to keep it at a certain level. And if you don't know, or maybe you had an unseasonably dry year and you did let your reservoir kind of restock for the season, and then it just happens to come at the wrong time, it's really hard to kind of make that decision sometimes.
This was a little late, they watched the lake come up to the brim and then decided to open the gates.
Right.
Rather than during the 3 days of rain, slowly letting it drain.
Yeah, which is better. Yeah. Yeah.
My question is kind of community related to that was brought up earlier in your intro and stuff like that. In some of these areas where there's like really critical dams, like is there any community outreach as far as like drills go that like can kind of like include them in planning purposes to like get them thinking about like what if there is a failure and what they need to do with it and stuff like that?
So not all of our dams are equipped with early warning, and not all of our dams anymore have tenders. But some of our key dams do have early warning, and they are managed by the individual regions and the water districts. It's a weird thing with reclamation because we own and operate the dams, but we don't own the water. And so it does require some sort of cross between the water districts and reclamation to make that happen. But we do have places definitely where we have sirens and drills and they do the speakers. There are a lot of phones now have the communication systems where they send out the alerts being like, big event, whatever. In Boise, I know the river system there that I work on, we've got 5 dams on the same river, just kind of up. And when they have these big storm events, they'll do these drills because there's downstream recreation, a lot of tubers and kayakers. And so they'll do these kind of annual, every couple of months things being like, we're expecting high rains, don't go to the boating areas today, this is a drill or whatever. And so there are some of that, but frankly, not enough. And to be honest, one of the areas that I've been trying to work more on is like, we have a lot of dams on BIA land, Bureau of Indian Affairs, so Indigenous tribe land, and they have nothing, no resources, nothing. And so we're really working on those areas because those are also really critical areas. And sometimes they have some really big infrastructure there. And so it's a work in progress, but it's tricky. Yeah.
I think we're a little bit over on time anyway, so why don't we think?
Yeah, Ellen,
Thank you.